Hey guys, we did this problem in class when we last were talking about calorimetry before your lab, and the bell rang right when we were finishing it up, so I just want to go through this one all over again. I also want to go through the next one, and then we're going to talk about bomb calorimetry, and then I'll post the problems from your book that I want you to do for homework over the weekend. So this says, when a student mixes 50 mils of a 1 molar HCl solution and then 50 mils of a 1 molar sodium hydroxide solution in a coffee cup calorimeter, the temperature of the resultant solution increases from 21 degrees Celsius to 27.5 degrees Celsius. We want to calculate the enthalpy change, so I'm trying to find delta H, for the reaction in kilojoules per mole. And that's specifically for, it says, HCl. Let's assume that the calorimeter loses a negligible quantity of heat, so we're trying to keep all of the heat in, and that the total volume of the solution is 100 mils. We know density is 1 gram per milliliter, and specific heat for water is 4.18 joules per gram Kelvin. Okay, so of course, for calorimeter, I automatically want you to always go to Q equals MCAP. Okay, now mass for this, we had 50 mils of HCl, we had 50 mils of NaOH. So since that density we said is going to be 1 gram per mil, my total mass then would just be 100 grams. So mass here would be 100 grams, so Q is equal to 100 grams. They also gave me the specific heat, and that's 4.18 joules per gram Kelvin. Okay. And then my change in temperature, if we go back to that, my change in temperature, we were going from 21 degrees Celsius to 27.5 degrees Celsius. So then our change in temperature is going to be 6.5 because we would do final minus initial. So 27.5 minus then the 21. So change in temperature is 6.5, and then that's just Kelvin, because that change in temperature is going to be the same whether it would be Kelvin or whether it would be Celsius. So the change in temperature could be in Celsius or it could be in Kelvin, and since this is in Kelvin, we'll make that to be in Kelvin as well. So if I do the math here, I should get Q to equal, let's see, and then that's in joules. We should get it to be like 2.7, and I'm going to change this to kilojoules. So we should get it to be 2.7 kilojoules, or 2,700 joules. But I also want to think about the sign for Q. Is Q going to be positive, or is Q going to be negative? Well, the temperature of the water increased. It went from 21 to 27.5. So then that means the system must have lost energy or released energy to the water to make the temperature rise. So since the system is losing that energy, Q here should be negative. Okay, but that just tells me how many kilojoules I have, and they asked me the enthalpy change for kilojoules per mole, and that's specifically of HCl. So right now I have the first part, I have that kilojoules part, but I want to think about this for HCl, and I know that we had 50 mils, I know we have 50 mils of HCl, and the concentration of HCl was 1 molar. So let me find how many moles of HCl I really have in this reaction. So I can do that because I know it's 1 mole per liter of HCl, and I want to know just how many moles, and that's in 0.050 liters. That'd be 50 milliliters. So if I do this, that would leave me with how many moles of HCl I have. So that should just be 0.05 moles of HCl. Okay, so now that I have that Q is equal to this, and now that I have how many moles of HCl we had in our reaction, I can just divide those two to get the change in enthalpy in kilojoules per mole. So we're going to do, to find delta H, I'm going to do a negative 2.7 kilojoules over that 0.050 moles of HCl, and then that should give you a negative 54. And that would be kilojoules per mole. So that would be my answer. Okay? So let's do another one. Let's look at what the next one says. This says when 50 mils of 0.1 molar silver nitrate and 50 mils of 1 molar HCl, hydrochloric acid, are mixed in a constant pressure calorimeter. The temperature of the mixture increases from 22.3 to 23.11. We want to calculate delta H for this reaction in kilojoules per mole of silver nitrate. We're assuming that combined mass is 100 grams, and then specific heat is 4.18 joules per gram degrees Celsius. Okay, so different reaction, but really ultimately the exact same thing. So as soon as I see calorimeter, let's go Q equals MCAT. Okay, and in this one we were, again, let me just write that. We were reacting AgNO3 with HCl. And then that, we had 50 mils of both at 0.1 molar of both. And then that one was at 50 mils. Okay, so let's go Q equals MCAT. So Q is equal to, they told me that since we have 50 mils of both, the mass is going to be 100 grams. I know specific heat, they gave me that, is 4.18 joules per gram degrees Celsius. And then my change in temperature, final minus initial, so 23.11. Minus, I think it was 22.30, yep, minus 22.30. Okay, so if I do that math, I should get 338, what is that, 0.6 joules? 338.6 joules, okay? And again, I want to think about silver nitrate and how it's reacting with HCl. So in this case, I'm going to look at my temperature change to determine what Q should be in terms of its sign. Is it positive or is it negative? So it says that the temperature of the mixture is increasing from 22.30 to 23.11. So because I have that temperature increasing, and remember I'm just really measuring the water that's in here, that means that system, that reaction is releasing off energy. So because of that, because that temperature is increasing, means the system's losing energy, so Q here should be negative. So it should be a negative 338.6. Okay, so, and that would be in joules. I want this to be in kilojoules though, so that would be the same thing as 0.3386 kilojoules, okay? But that's only a piece because I need to know that change in enthalpy, and that change in enthalpy was specifically for silver nitrate. Let's go back, because it says, calculate delta H for this reaction in kilojoules per mole of silver nitrate. So I need to now find, I have this first piece, I have the kilojoules part, I need the moles of silver nitrate part. So I know that we started off with 0.1 molar, or moles per liter, of silver nitrate, and then I have 50 mils of it, so let's multiply that 0.1 times 0.05 liters, and then if I do that, that will give me 0.005 moles of silver nitrate. So now that I have my kilojoules part, I have the energy part, I now have the mole part of silver nitrate. If I divide these two numbers, then I'm going to get my change in enthalpy for this particular reaction. So if we do that, we should get around like 68. So delta H should be around 68 kilojoules per mole. Okay? So these are what your calorimetry questions are going to look like. They're all going to be based on Q equals MCAT, because I can find change in enthalpy, because almost always change in enthalpy is going to be equal to Q. I'm going to have to place the sign in front of Q to determine, is it going to be an endothermic reaction or is it going to be an exothermic reaction. And then I'm going to always have a concentration and an amount of volume so I can find moles, and then I can just divide those two then to find that change in enthalpy in kilojoules per mole. Okay, there are some times on FRQ questions, these will all be broken down into steps. So I'll give you this whole problem, and then in step A it will say, calculate the amount of heat that is released or absorbed for this reaction. And so ultimately you would just be finding Q. And then in part B, it would say, tell me what the sign convention for Q would be based on the problem above. And then we could say, since temperature is increasing for the water, that means the system must be releasing energy, so the water is gaining that energy. So since the system is releasing, it's going to be an exothermic process, so Q must be negative. So that would be like a part B. And then a part C would be, calculate how many moles of silver nitrate are involved in this reaction. You did that here. And then the last part would be, calculate the change in enthalpy in kilojoules per mole. So then you're going to take your answer that you found in A, divide it from your answer that you found here with the moles of silver nitrate. So they'll try to walk you through step by step. It's just kind of easier if we know all of those steps. Okay, lastly, we're going to talk about bomb calorimetry. Reactions can also be carried out in something called a bomb, and usually combustion reactions are going to be what's carried out in a bomb calorimeter, and that's just because they can release so much energy or so much heat. So what happens is that a substance is placed in a small cup within an insulated vessel, and we call that a bomb. So if I'm looking at my picture here, this is going to be the bomb, this is the reaction chamber, and then that bomb is inside a very, very well insulated vessel. So the bomb is made to withstand very high pressures, and it has an inlet valve for adding oxygen, and then we also have these electrical wires, these electrical ignition wires that are in there as well. Okay? So after the sample has been placed in the bomb, we seal this little chamber here with pressurized oxygen. After we place that bomb and seal it up, we cover the calorimeter, and then we cover it with a very specific amount of measured water. So I'm going to have a specific amount of measured water around that bomb that's inside that insulated container. Okay? The combustion reaction is going to be initiated. So how do I make this sample go through a combustion reaction? Well, I do that because I'm going to pass an electrical current through these leads, through these ignition wires, and then when that wire becomes hot enough, it will ignite this sample so that way it will combust. So we're just trying to force this sample to combust so then that way we can measure then that change in enthalpy. So the heat, when it's released, the heat released when combustion occurs, of course it's going to be the exact same thing like the other calorimeter that we did with the coffee cup, in that any energy that this releases, the water around it is going to absorb. So I can monitor that through the use of my thermometer. Okay? So then to calculate the heat of combustion from the measured temperature increase, we're going to have to know something called that total heat capacity, or what we would call C-cal. So all we're doing is, it's the exact same thing ultimately as the coffee cup calorimeter. The only difference is I have that reaction in a little contained vessel. We call that a bomb. And then I'm going to ignite that reaction through these wires, just heating them up. So then I can get this to combust. When it does combust, it will release energy to the surrounding water, and I can measure that temperature increase by the thermometer. Okay, so when we use a bomb calorimeter, we can measure the reaction. We can measure the heat of the reaction by taking C-cal times that change in temperature. Okay, so let's maybe do an example of this. This says that the combustion of methylhydrazine, which is CH6N2, and that's just liquid rocket fuel, produces nitrogen gas, carbon dioxide gas, and then water. When 4 grams of methylhydrazine is combusted in a bomb calorimeter, the temperature of the calorimeter increases from 25 degrees Celsius to 39.5 degrees Celsius. In a separate experiment, the heat of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. Calculate the heat of reaction for the combustion of 1 mole of CH6N2, or methylhydrazine. Okay, because we're using a bomb calorimeter, we're going to immediately go to Q is equal to Ccal times change in temperature. And we're leaving that negative here because when that temperature change, as long as the temperature change has increased, then that will be a positive number, so that Q reaction should be a negative. So it means just releasing energy. So if I go back, let's go open a active inspire board here. I know Q reaction is equal to a negative Ccal times change in temperature. Okay? In that problem, they gave me what Ccal was. Now in our lab, that's what you had to experimentally find. You're not going to be experimentally finding that on an AP test. We just did that in the lab so that way we could have practice of how do we find Ccal. They gave me Ccal because they said in a separate experiment the heat capacity of the calorimeter is measured to be 7.794 kilojoules per degree Celsius. So I already know that Ccal is 7.794 kilojoules per degree Celsius. And then we also know that that temperature changed from 39.5 degrees Celsius, it started at 25 degrees Celsius and it ends at 39.5. So to find that change in temperature, I'm going to do final 39.5, that's degrees Celsius, minus 25 degrees Celsius. Okay? So then if I do that math, Q reaction should be equal to a negative 113.0 kilojoules because the degrees Celsius would end up canceling out. Okay, so that's the heat of the reaction. But they asked me, they told me to calculate the heat of the reaction for a mole of CH6N2. I don't know how many moles of that I have because they didn't give me that. They told me grams. So I know that this reaction is going to take place, 13.0 kilojoules. They told me this will take place in 4 grams of the C into H6. Right, so I have 4 grams of this, and that's what's going to change that temperature change. So I need to figure out how many moles it will be of this. So I want in kilojoules per 1 mole of this. So I'm just going to use molar mass of CH6N2 to then figure out how many kilojoules in 1 mole of this. So I want grams of methylhydrazine up here, H6N2, over a mole of CH6N2, okay? So I know that in 1 mole, I can use my periodic table then to figure out that this should be 46.1 grams of that. My grams would then cancel. I'd be left with in 1 mole how much energy it would be. So if we do that, we should get it to be a negative 1.30 times 10 to the 3rd kilojoules, and that will be per mole. And it's just per 1 mole of that methylhydrazine, okay? So very similar to doing something with a coffee cup calorimeter, only in the fact that they'll give you this, you'll know that change in temperature, so then ultimately I can do this part, but they'll probably always give it to you not in 1 mole. They'll give it to you where you have to do something with molar mass here. So I manipulated, I had 4 grams based on this amount of energy, but I need to know how much that would be in 1 mole of methylhydrazine, so we did that here. Okay, so because the volume in the bomb calorimeter is constant, so because the volume in the bomb calorimeter is constant, what is measured is really the change in the internal energy and not so much the change in enthalpy. Usually in most of the reactions that we do, the change in internal energy and the change in enthalpy is really so small, the difference between the two is so small that we just consider it to be negligible. So usually whenever we're finding delta H, because most of the time we kind of forget about work being done, we really just think about it as the change in internal energy. And that's actually what we're finding instead of finding this. But for us, we're happy with it because the difference is so small anyways that doing things like this or the coffee cup calorimeter are totally working out well for us. Okay, so we did Hess's law. Sorry guys. We did Hess's law today in class. On Monday, we're going to do a couple more practice problems with Hess's law. We'll talk about your homework questions that you have from Chapter 5 from your book and what problems maybe that we had with them. And then we're also going to finish up Chapter 5 and do something really easy, which is just the enthalpies of formation or standard enthalpies of formation. So we'll start here on Monday, finish up Chapter 5 on Monday, and then we'll also talk about any type of problems that we have from that chapter. If we get done with Chapter 5 Monday, we're just going to go straight into Chapter 10, which is all about gases. So then hopefully we can bridge Chapter 5 and 10 together. Okay, everybody have a really great weekend, and I will see you on Monday. Bye!